All right, we'll get started. As our next speaker, as he's already said, is a co-organizer of the workshop, Neil Immerman, towards capturing order independently.
Okay. Well, thank you, Nishant. I'm really delighted to be here, and this is, for me, this has kind of been the semester from hell, so I just want to apologize. Well, I'm teaching, I was explaining this to a bunch of people, but I'm teaching 155 UMass sophomores what mathematics is, what a proof is, what a definition is, what a lemma is, what induction is, what ordering is, what an equivalence relation is, what a graph is, and so on, and making them prove things about it. And in my spare time, I'm trying to do other things. So it feels like a wonderful vacation to be here. And I wanted to give a talk about something that many of you by now here have already surpassed, and there's a lot of understanding of this. But there's a problem I want to talk about that I think is really, really basic, really important, really interesting, and there's been so much new development about it. So I want to tell you a little bit about it, and so Martin, I'm going to talk some about perhaps even prove the Immerman theorem from so many years ago. Martin Furrer is here. Jinyi Sai said, maybe I'll come. And then that was my last email from him. So I don't see him today, but maybe he'll be here tomorrow. And of course, I'll be talking about choiceless polynomial time, and Andreas Blas and Yuri Gurevich are here. So it's great. So I just, basically, I have a lot of slides, and I'll just skip through them if this works, just to talk about where I'm coming from, which is descriptive complexity, which I'll remind some people. Just basically, it's a way of viewing, from my point of view, viewing computational complexity from a completely logical point of view. So in complexity, we're always talking about decision problems. Does this input have a certain property? In descriptive complexity, we're saying, well, how hard is it to express that property in some kind of formal language? And instead of saying how much time or space or processors, blah, 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 do you need to check if the input has a certain property, I want to say how rich a language do I need to express the property? So the property is the property of the input. So the input is a finite structure. And so we're doing logic over finite structures, which most logicians will tell you is just trivial. And it's not trivial, it's different, and it's much more like combinatorics. And what I've found over the years is that anytime anybody, I hear a question about computer science, I can translate it to this language, and then I can sort of understand what it says. So there is, and that can be done automatically, although it's hard for most people to do. But this is just another approach to computation, which works for logic. And so many of you have seen this many times before. It's sort of my favorite diagram of what the world looks like. And does everyone know my story about Daniel and the cover of my book? Not everyone. Okay. So I finally, after many years, wrote a sort of monograph about this stuff, and it was in the Springer series of whatever series it was. All the covers are pure gray. And the editors who were at Cornell, in answer to my question, said, OK, you can put a diagram on the cover. So I came home, I was really pleased. And I said, and Daniel, who's like my son, 10 years old then, wanted to know what it was about. I said, well, this diagram sort of explains a lot of what's going on in the book. And Daniel looked at it and he said, that's very good, Daddy. That means no one will buy that book who shouldn't. So anyway, let me say 2 words about this diagram. I could just leave the diagram here forever. And so basically, so in some sense, there are all these complexity classes, like this is non-intrinsic polynomial time, which this whole field of descriptive complexity started with Ron Fagan, who was thinking of coming. Well, we invited him, but I guess he's not here. Not going to come. Oh. And so Ron proved in his PhD thesis, I believe, that NP is equal to second-order existential. So a completely logical characterization of NP. And I thought I heard about this a couple of years later when I was a grad student, and I thought, wow, no one's going to be able to prove that Turing machines can't do a certain number of things like this, but logic, we have all these tools. So I was excited about that. And I also thought, I'm never going to prove something's not second-order expressible. That's too powerful. So I looked at building up from first-order logic. And originally, I thought that first order was really, in some sense, too weak to be interesting. So your input, well, of course, Howard just talked about this. So first order includes regular properties. So it's not too weak to be interesting, but it's pretty weak as a complexity class. And it turns out later, I found out that first order corresponds to constant parallel time when you have polynomially many processors in a concurrent model. So it's actually a very nice model. And coming up here, we found out that increasing the number, basically the iteration depth of a formula or an inductive definition is exactly parallel time. And what's very nice, well, I can't talk for the whole time about this diagram. But anyway, so we have all these characterizations, and all of these depend upon an ordering on the universe. So of course, being logicians, you're all familiar with inductive definitions. And from my point of view, inductive definition, the most standard one is I have a graph I want to describe, say, E star, which is the reflexive transitive closure of E. And of course, that's not first order expressible. We can define it by inductive definition. So my inductive definitions are typically positive. So the relation being defined only appears positively. So in that case, we have the Tarski-Nasser theorem, which is pretty obvious in the finite case. It says that in a polynomial number of iterations, you'll reach a least fixed point. So we have a least fixed point operator which formalizes making inductive definitions. So from this, we get the theorem that says polynomial time is equal to exactly first order logic plus inductive definitions. And another way of thinking of that is the least fixed point operator in this setting is just a polynomial iterator. It's taking a sort of a fixed block of restricted quantifiers and iterating it polynomially many times. And this is the way I often think of it. So just, whatever that means, you take a fixed block of restricted quantifiers, iterate it with the same variables, so it's a bounded number of variables, polynomially much. And that's polynomial time. And that depends on the fact that our input structure is ordered. So mostly what I'm going to talk about today is this ordering issue, which I think is really fascinating and very relevant to this symmetry workshop. And by the way, graphs, as I tell even my sophomores in discrete math, everything is a graph. That's the only thing you have to look at. You can understand everything as a graph, so we don't have to go beyond graphs. And it's a theorem in first order logic, everything is a graph. Okay. So we'll just talk about graphs from now on. And as I said, the above theorem requires ordering. In some sense, our input is a graph, but from a pure mathematical point of view, what's a graph? It's a set of vertices with an edge relation on it. It can be directed or undirected. But from a computational point of view, I want to input that graph, so I need vertex 1, vertex 2, up to vertex n. They have to be ordered. That ordering has nothing to do with the properties of the graph. I don't want an algorithm to take that graph and use the ordering and do something special because of the ordering. Okay, so I'd like to know, I have my algorithm, I'd like to know if it's order independent. That's of course undecidable, as any question about Turing machines is undecidable like that. But what's really what we care about is order independent. Why don't you just input a graph without an ordering? That's impossible. Okay, and I've thought about this for years, and it's really funny. What even is a graph, this mathematical concept? A graph, a set of vertices that's unordered. You can't show it to me. Draw it on the board, that's an ordering. Give it any labels in any language you know of, that's an ordering. So you can't even talk about, it's not just the computer's fault. You can't talk about, in a specific way, a graph without an ordering, as far as I know. And I'm sure someone will contradict me, and I'll have an example of a way that maybe you could. But a finite graph that's not ordered, how do you exactly say what it is? Which vertex has the edge to which other vertex, if you can't name them in a way that sort of gives an ordering. Okay, so this is a kind of fundamental problem. Any input to a computer, as you know, it's just a binary string, so it comes in ordering, and all the things you can do in polynomial time are all the things you can express in least fixed point. But now here, we're really interested in this issue of, is that algorithm order independent? Is there any way to recursively list out all of the order independent polynomial time properties of graphs? It's easy to introduce all the polynomial time properties of ordered graphs, the things we usually get, because you just put a clock on the computer. If it stops, I'll say, okay, this is an algorithm that runs in n squared, and I can prove that because after n squared steps, it stops and says no. Okay, so you can list out all the polynomial time properties of ordered graphs. Can you list out all the polynomial time properties of graphs of order? And that's completely open. And this is sort of the question. Okay, and I've conjectured yes, Yuri's conjectured no, and that was many years ago, and we still don't know. Okay, so this is the question I'm really, really interested in. And as I say, ordering is really necessary. Okay, and of course, for graphs, the ordering is irrelevant. Right, so the program is wrong in some sense if it depends on the ordering. Okay, and I'd like to know that. So what we would like to do is a theorem like this so-called Immerman-Vardy theorem, but for unordered graphs. So is there some way to capture what I'm calling here order independent P? So OIP in this talk is just order independent P. Does everyone understand what it is? All the polynomial time properties of graphs that are order independent. Okay. Any question? There's none enough questions yet. Okay. We'll try. Okay. And just pointing out, so when you first look at this, okay, first order logic with all these fixed point is P. Question, great. Yuri.
Maybe instead of OIP, it should be just P. This is the real.
Exactly. No, I agree. But that's, no, exactly, yes. I'm just trying to capture P, but then people say, oh, that's already been done. So I call it OIP. But no, I totally agree. I'm just trying to capture P, that's right. And I don't want to tell anybody we haven't done it yet, though. Okay. So, but if you take this language and just remove the ordering, it's just too weak. First order with least fixed point and no ordering on graphs. For normal graphs, it's okay, you can walk along the edges. But for an empty graph with no edges, it's kind of a horribly weak language because any fixed formula in least fixed point, as I said, it's just one fixed formula with a fixed number of variables, iterated, but it still only has a fixed number of variables, so it can only talk about k objects at a time. So even something as simple as saying, does my graph have an even number of vertices? Or if you know how to count the number of the universe, does it have an even number of edges? Those are not in this language. Okay, and that, by the way, is so even is an example of something in order independent P, but not this candidate language without the ordering. Okay, so that certainly is our first trial, first order without ordering in fixed point is not strong enough. And question?
Yeah, so sorry if this is
no go ask.
heresy, but why do we? I mean, why should polynomial time be important? And, like, why would we care?
Oh, why would we care? Oh, interesting. So. Oh, yeah, okay, great. That's what this talk is about, so let me see if I can try to express it. So for me, I mean, it's so deep-seated, it's going to take a minute or two to get it out, but I can tell you. One of the issues is really, I want to know, well, one thing I wanted to do when I was a kid, like a grad student, I was trying to prove P not equal to NP. No one knew at that time it was so hard. And to do that, I was kind of using errand for per se games. But the problem with errand for per se games is that in some sense, they lose all their effectivity once you have an ordering. Because you can just say, this is vertex 17, this is vertex 3, and there's an edge there or not. So you can't distinguish different graphs with ordering. So my goal was really to play errand for per se games without the ordering, but in a context that it was strong enough to capture polynomial time. And then I could prove P is not equal to NP. So that was my original goal. And then there's a whole database community who had a sort of theology that the algorithm should be independent of how the data is actually stored on the disk. And that means order independent. So there's a lot of interest from the database community for order independence. So that sort of got it going. For me, it was always this basic question. But it's the other question is just, somehow I have the structure, I would like to capture its essence without ordering. And it seems like a question logicians would like to know. The polynomial time is an afterthought, which I'm really interested in. But even just that question, let's capture the essence of the structure without the ordering. Yeah?
In defense of that theology,
Yeah, sure.
lack of order independence allows optimizations that make queries run faster.
Okay. So, no, order independence is great.
It's the god of efficiency that theology.
I never thought of it that way. Okay, great. So there's two reasons at least. Okay, so this is the abstract question I want to do. I want to say, okay, how do we characterize properties of graphs that are order independent? How do we list out all the order independent polynomial time properties of graphs? Okay, I think it's really interesting. I'll talk about it more, see if you agree. Okay, so, and I just want to mention, how do we prove even is not in first order without ordering least fixed point? I sketched that. With Ehrenford per se games. So everybody knows what Ehrenford per se games are? Yeah. Okay, so they're fun, and for some reason I call the players Samson, Delilah instead of Spoiler and Duplicator. But if you haven't played them before, you can see them being played right now. And the key thing about the games is that let me say this notation: G tilde super K sub M H means that Delilah, the duplicator, has a winning strategy for the game that goes for M moves and has K pebbles. So pebbles correspond to variables. And so if Delilah has a winning strategy for the M move K pebble game, I say G tilde K super K M H. And the fundamental theorem of these games is that Delilah has this winning strategy on the K pebble M move game if and only if G and H agree on exactly all first order formulas with at most K variables, so the language L super K variables and quantifier depth M. So a move of a game is exactly a one more nesting of quantifier depth. Number of fingers you have on the board, pebbles, is the same as number of variables. Okay. So from that, it's obvious that you can't say even. To say even, I need a linear number. I need a variable for every single vertex. Otherwise, I can't distinguish these two. Does it make sense to everyone? Great. Okay. So, and again, to answer this person's question again, what was your name? Siddharth? Yeah. Okay, so Siddharth's question. I really want to be able to play Ehrenford games in an effective way that has something to do about computation, but doesn't use the ordering that messes me up. Okay? That's really what I want. And so one thing, so since just taking out ordering wasn't working, the counterexamples were all in terms of counting things, even number of edges, majority of the bits are on, things like that. So I thought, okay, let's just add counting quantifiers. So we're going to think of our logic now. The graph is just n vertices, but there's no ordering on the vertices. But it's a two-sorted structure, so I have numbers too. Let's say numbers from 0 to n. And on the numbers, there's the usual arithmetic. I have ordering, plus relations, times relations, what have you. And then I want to be able to count. I want a counting quantifier. I want to be able to say there's 3 vertices, or 5 vertices, such that something. And more modern treatments, due to Martin Grohe and others, instead of counting quantifiers, they just use a counting term. So number x such that phi of x means that number, the number of x's such that phi of x. Okay, so I'll use that notation in this talk. Okay, so what I want to have is, so now I did it to myself too. So now. I see. I just pulled that out. Great. So, I'm sorry. So let me talk for a minute while that comes up again. Great. Okay. So is that okay? I can now count, and I'm still only talking about order independent properties because my graph is not ordered, but at least I have counting now. And now I can say even, for example, it's easy. I just say there exists a number I, which is even, and or the number of x's such that x equals 2i. So the number of vertices is even. Clear? Okay, so I have counting, and let me define C super k to be first order logic with at most k vertex variables, x1 to xk, but I can count. Okay, and so counting means I have counting quantifiers, or for this talk, just these counting terms. And then we can talk about FPC, which is first order logic with a fixed point operator and counting. Okay? And the reason I'm talking about C super k is that each formula in this language, which has a fixed point operator, so it iterates formulas and they have counting, has a fixed number of variables. So every particular formula in here is in CK for some k. And I'll play Ehrenfurt-Fisse games with the CK. And I have like, fineness. Oh. Okay, so let me just move a little bit. There were various standard graph isomorphism algorithms that people were looking at, starting with, for example, vertex coloring. So Babai calls this the Weisfelder-Lehmann method. So you can color vertices by how many, what their degree is. And then, so for example, these blue ones are of degree 4, everyone else is of degree 3. And now at the next round, that's the quantifier depth 1 formulas. At the next round, this one has one blue neighbor and one black neighbor. This one has 2 black neighbors. So at the next round, they get different colors. I don't know if you can see them. These are blue, these are magenta. Okay. And so on. And then if you do stable coloring, that's just computing the C-type. And each round of the stable coloring is a step of the C-type. Now, very interesting, Babai, Erdos, and Selkow showed a long time ago that with high probability, you take a random graph and you color it, just vertex color it, 4 steps. Every vertex has a unique name. Okay. Which means you've put that graph into a canonical form, because those names, by the way, are alphabetically ordered. So now you have an ordered graph, and each ordering has a specific meaning having to do with the graph. So what that means is that graph canonization for almost all graphs can be done in linear time. A very simple algorithm. Okay. So there is this algorithm, and so graph isomorphism is very easy for random graphs. However, for general graphs, graph isomorphism is unknown. And of course, last year, there was this, Babai with wonderful, deep, difficult to understand for me at least, group theoretical algorithms moved the graph isomorphism upper bound from n to the square root of n down to n to the polylog n. And his estimate right now, it's n to the log to the 7th n, but I'm sure that 7 won't go down. But he and several other people were organizing a Dodgestall workshop, the first ever, last December, on graph isomorphism. And maybe for that reason, Babai wrote his thesis on graph isomorphism. Maybe for that reason, he worked a little harder, and he got this result, which he got to present at the seminar. And I had the pleasure to be there. And that's part of why I'm sort of re-looking at this now. I think we're ready to solve some of these problems, in my opinion. Not me ready, you ready. So anyway, 3 minutes? What do I have? 3 minutes, okay. Okay, so C2 and C3, there's nice polynomial time algorithms to check, just using these Ehrenfurt-Fisse games, whether 2 graphs are C2 equivalent. So almost all graphs are C2 equivalent. For almost all graphs, they're C2 equivalent only if they're isomorphic. Okay? And it doesn't work so well. C2 doesn't work for regular graphs, but C3 does. For almost all regular graphs, they're C3 equivalent in a short number of steps only if they're isomorphic. Okay? And you can test CK equivalence in polynomial time. So a whole bunch of Russian computer scientists, the group started by Weisfelder-Lehmann, were trying to work and see, well, maybe there's some constant, like 3, such that C3 equivalence, in other words, labeling pairs, was enough to do graph isomorphism. Or maybe it was known for 3 and it was open for 4. Okay, so labeling triples. Whether C4 equivalence was enough for graph isomorphism, in which case graph isomorphism would be in polynomial time, and we'd have a polynomial time canonical algorithm, canonical form for all graphs, in which case OIP and P are the same, because you can just take the graph, canonize it, and then run your algorithm. So it's automatically order independent. So if graph isomorphism or graph canonization turns out to be in polynomial time, then P and OIP, just the same thing. Problem is solved. Doesn't necessarily help me prove P not equal to NP, but still it's a nice solution. Does that make sense, everyone? And that could be true. Okay, we still have no idea whether graph isomorphism is in P or not. At least I have no idea. I don't think too many people have a strong idea. I'm sort of hoping that the right bound is n to the log n. But yeah. Anyway, so that was. So it was an open question. Was fixed point with counting equal to order independent P? It was an open quite a while ago, and the paper with Martin Führer and Jin Tsai, we showed a lower bound that's the so-called now Tsai Führer Immerman problem is not polynomial time. So basically, it was open whether C4 characterized all graphs, and what we showed is no, you need a linear number of vertices to characterize all graphs. And let me just show you the picture. Okay, that's sort of a nice little core gadget that has a bunch of automorphisms. This is a graph. The red vertices on top, the green ones on the left side, and the blue on the right side, and the middle ones are maybe black or magenta. So this is a graph of color class size 4. So in some sense, I can't sort of automatically distinguish between these 4 points. Otherwise, I have a graph that's going to be ordered up to color class size 4. So it's almost ordered, but not quite. And what we showed is, okay, you can put that gadget together in a graph that has high separator size, and then maybe flip one of these edges in this huge graph. So this is a huge graph of color class size 4. So it's almost ordered, except some 4 tuples, I can't tell the difference. And yet, you can't tell the difference. You can't tell, is there an even or an odd number of flips? Okay, so you can't do isomorphism on those simple graphs, even though it's a linear time, very simple property. If the graphs were ordered, you could see whether or not the edges were flipped. So this was the so-called Cypher-Immerman example. And it's fun to play the Aaron per se game, which if we had another hour, we could do. And so we showed, okay, this simple property, now called the Cypher-Immerman property, is linear time. It's very simple, but it distinguishes. It's not expressible in fixed point with counting. But then there was all this fantastic work. Anuj Jara has a wonderful survey paper in Siglog newsletter from a year ago, something like that, about the amazing power of FPC. You know, after this lower bound, I sort of forgot. I loved that language, but I said, oh, it didn't work. But it turns out FPC is actually very, very powerful and really interesting. And so, for example, Martin Grohe, with a long series of work, he showed that planar graphs, there was a fixed number of variables. I don't know what it is, 7 variables that characterizes planar graphs. So 2 graphs are C7 equivalent, they're isomorphic. And then he and his students proved a few more things, and finally they proved that for huge classes of graphs, any class of graphs that excludes a minor is characterized by CK for some K. So fixed point with counting is very, very good. It captures polynomial OIP on any such class of graphs. Any graph with a bounded genus, any graph with a I think bounded degree, and any graph with bounded tree size, and so on. So quite amazing.
Not bounded degree.
Not bounded degree is not no?
Well, no, CFI is already.
Oh, sorry. CFI is bounded degree. Thank you. See, I would just. Okay, thank you very much for keeping me honest. I appreciate it. So not bounded degree, even though bounded degree, of course, is polynomial time. So that's that, and that raises an interesting question, which Anuj students and postdocs have been working on. What do we have to add now and for me, what do we have to add, or what other language can you take fixed point FPC and add to that to get this problem and all the other problems they were just squeaking out? And I mean, so Yuri and Andreas's choiceless polynomial time language, Ben Rossman and Anuj and one other person proved that was strong enough to just express this property. And Anuj and others introduced rank logic, where what we'll add is have a sort of unordered matrix and take its rank as a new operation. Add that to fixed point plus counting, you get this property. But are those two capture order independent P? Maybe, we don't know. And you guys should figure it out. Okay.
Any questions?
Okay.
No, I think people are hungry.
Okay, you must have a question. Come on.
I think we'll.
Oh, just lunch? Okay,
Yeah,
okay, okay.
Break for lunch now.
Okay.
Back here too. Thank you.